So I'm going to tell you about our work in image segmentation and I picked this particular piece because I think it resonates well with the tutorial. So it's a little challenge for you to think about as I talk through these points, and I try to structure the lecture so that it images what we did in the morning in terms of thinking about how to set up the framework. So in some sense, think of this as a not reading group, but listening group, and try to figure out what the components are. Now, the huge amount of credit goes to Adrian Delka and Ramesh Sridharan, who are two graduate students in my group, who actually have done most of the work on this project in collaboration with Natalia Rost, who is a clinician, stroke clinician at Mass General Hospital. So the title in the program is humongous, and I discovered that I can't actually fit it on the slide, so you get a shorter title, Segmentation Analysis of Stroke Images. So I assume that not many of you have seen stroke images, so let's just understand what the problem is. The image on your left is an image. It's an axial image of the brain of a patient who is going through an acute stroke phase, meaning that it's within 48 hours of the onset of stroke. And this is part of a very large study, multi-institutional study of stroke, and trying to understand the genetic causes of stroke. But what we're looking at is what's so-called T2 flare images. These images emphasize certain properties of the tissues that are of interest in the study, and it's not the acute stroke. So acute stroke actually doesn't show up in these images, and the reason why we want to study these images is because they show up two interesting things. Well, one interesting thing and one nuisance that we're going to get rid of. It's the usual story in medical image analysis. So these yellow faint lines outline, it's a manual segmentation of what's called white matter hyperintensity. The real technical term is leukorrhiosis. Leukorrhiosis is sort of this elusive notion of damage to white matter due to some cerebrovascular problems. So some people think that it's microbleed, some people think that it's degeneration of sort of vessel structures. Nobody really has a great idea of a great model of leukorrhiosis. But what we know is that all of us get it as we age. It's a normal part of normal healthy aging. The problem that people have noticed is that patients who have stroke, who have more leukorrhiosis, recover worse than the ones who don't. So in the clinical domain right now, leukorrhiosis is accepted as sort of a marker for cerebrovascular health. And so the question now is, can we analyze leukorrhiosis and its appearance in the images together with genetic and clinical information? But in order to do that, you need to acquire thousands of patients, because we're talking about genetics where the signal is so small that you need lots of patients, which means that you need to segment thousands of images, which is impractical to do manually, and that's where we started working on this problem. Okay, and so it shows up sort of around the ventricles. This is fairly typical case. And so you'll see little spots. To segment it manually, what people typically do is they play with the threshold, because it does show up brighter in these images than normal white matter tissue. They play with the threshold. They set the threshold in the slices where there is leukorrhiosis until they're satisfied, and the threshold is roughly different for every person. And then they go in slice by slice and manually remove the islands that are in the areas where they know that that's irrelevant, okay? Sounds like a fantastic job for a graduate student, but instead we decided to actually write the algorithms to do it. Okay, so the faint lines in the blue here outline something that looks bright, so it could be mistaken by the algorithm as leukorrhiosis, but in fact, it's what's called chronic stroke. It means that this patient had a stroke, a small stroke before, and the residual of that shows up in these two images, while the acute relevant stroke doesn't, okay? And so the fact that acute relevant stroke doesn't is great, because then you could segment the leukorrhiosis and study it separately from the stroke lesion. The fact that chronic stroke shows up is bad, because suddenly you're counting all the voxels that a stroke into this very different thing, which is a chronic acquisition of damage over the years. Okay, and so here are some images to show you how challenging this problem might be. These are all examples of stroke. So shape modeling, which you'll hear about, I think on Wednesday or Thursday, is not going to really work, because the shape is so variable that at least by looking at it, we haven't been able to figure out how to parameterize it or how to model it so that it would tell you something about what the stroke looks like in the next image. Okay. we can learn something about the spatial distribution of things. So here are some examples of Licheriosis segmentation. Again, in faint yellow lines done by experts. So they sort of always clump up around the ventricles. This is an interesting one because see how speckled it is? Basically what happened here is that this Licheriosis stuff is not an object, unlike what we were talking about in the morning. It really is sort of change in the tissue properties. So when you threshold, you get the speckle, but they think that that's the real phenomenon, and so we want to study it. Replicate the segmentation technique and study it. Secondly, here's some chronic stroke that shows up. So if the algorithm segments this as Licheriosis, it's a problem because suddenly this person has lots of Licheriosis, so to say, but it's not true. Okay, here's another example image that illustrates a point. You could say something close to the ventricles would be Licheriosis, something farther away would be not. That doesn't work either because here, for example, all of this is Licheriosis, okay? And so roughly from talking to clinicians and staring at lots of images that they have segmented, we've devised sort of two rules, which is that Licheriosis shows up close to the ventricles and it's kind of roughly symmetric, but not precisely symmetric or anything like that. And stroke is not, and it's sometimes compact, but sometimes not. Okay, so this is the problem. My goal is to segment Licheriosis while separating it from stroke. If you look at intensity distributions, they're so close to each other that there's no hope of doing it by looking at intensity alone. We are going to have to do some spatial modeling. So the image term, remember from the morning, will be a standard image term that everybody uses, and the spatial term is where most of the work will happen, or a prior term, where we will craft it to tell us that the segmentations look like what we expect. Okay, and so we're going to use two facts. One of them is that Licheriosis occurs roughly symmetrically. We're not going to hard code it. We're going to actually learn this from images because we found that we don't know how to code it better than what the images tell us. Sort of coming up with hard rules is harder than learning it from the images. It's a little bit showing it's a little bit connected to what Ramin was saying. Sometimes the task of learning from images, if you have the right representation, is easier than figuring out what the rule would be that summarizes it. And also, both Licheriosis and stroke show up similarly in these images. Okay, and so this talk will follow a very simple outline. I'll show you our generative model that says what the segmentation should look like. Then I'll talk about the optimizer we use to actually solve it. Then I'll show you results and show you just a little bit of our preliminary analysis of population study in the context of population study of these segmentations, which is not exactly the topic of the talk, but it's sort of a nice component of where we're going with this. The goal is not just segmentation, it's actually figuring out something about the disease. Okay, and so our approach is very similar to EM segmenter. For those of you who know it, we will modify sort of the spatial term to make it work. For those of you who don't know it, on Wednesday we're going to have a reading group that actually talks about one of the original papers that discusses the original paper. The basic idea is to cluster the voxels in the image into different groups and call one group healthy, one group Licheriosis, one group stroke, okay? So if all of them had different intensity distributions, would be golden, because we would cluster in 3 classes and say the brightest one says stroke, then there is Licheriosis, then there is healthy tissue. But of course, in our problem, stroke and Licheriosis share the intensity, so we can't do that. So we are going to do clustering. Basically, EM is, you can think of it as soft clustering, where you get probability of being assigned to a different class. We're going to do this clustering subject to spatial constraints. And so our spatial constraints will be the following. Licheriosis distributions will come from a PCA model, principal component model, that generates spatial distribution. So we'll abuse sort of the term shape to mean spatial distribution, because it's not that we're modeling the shape of a little speckle, we're modeling the shape of the distribution in the images. And then if it's not Licheriosis, then it's either stroke or healthy tissue, and we'll just learn that from the images. So in some sense, if you think about this, if I gave you a segmentation of Licheriosis, then the problem would be easy to segment stroke from healthy tissue, because their intensity distributions don't overlap that much. So you could cluster the voxels roughly into 2 classes, except for we're going to estimate all of this as part of one generative model and one algorithm that does it. Okay, so now that intuitively we understand what's going on, let's get formal with it. So this is the trick that I mentioned in the morning. we're going to assign a vector of 3 entries to every voxel. And these 3 entries in our generative model are constrained so that only one of them is 1 and the other 2 are 0. And these entries mean that if there is 1, say in the first entry, it means that this voxel is leukorrhiosis. If the entry is 0 in that, it means that it's not leukorrhiosis, and so on. Right? So because we have only 1, it tells you unambiguously what class it is. Of course, it's great for the generative process, but when we're estimating it, we're going to estimate the probability that the first entry is 1, or the second entry is 1, or the third one is 1. So we're going to end up with numbers between 0 and 1 that will give us some confidence in it. Okay, so Cx is a vector in pixel x that tells us what voxel it is. Now, once I've generated it, and this little c tells me if it's 0, 1, or 2, right? Leukorrhiosis, stroke, or healthy. So for example, if in a particular pixel, the class that is equal to 1 is leukorrhiosis, then the intensity is Gaussian with the mean that corresponds to leukorrhiosis and standard deviation that corresponds to leukorrhiosis, okay? So this will give us the image term, right, in our distribution, because I'm going to multiply everything by likelihood, take the negative log, and minimize that. And so this is a very standard approach to this model. Okay, and most of the interesting stuff will happen in the spatial domain. And so here's the generative process. As I already said, we're going to generate whether it's leukorrhiosis or not based on the PCA model. I'll tell you in a second how we do it. And then if it's not leukorrhiosis, then it's either stroke or healthy tissue. And of course, we'll want everything to be smooth, meaning we'll put a Markov random field prior on everything, saying that neighboring voxels like having the same pixel, the same label. Okay, formally, I'm going to define a vector that is a prior on being leukorrhiosis, stroke, or healthy tissue. And the way it works is, for now, I have an image, mx, that tells me in every pixel what the probability is of that pixel to be leukorrhiosis. Okay? So every pixel is 0, 1, between 0 and 1, and that's the probability of being leukorrhiosis. Now, so this is the probability of being leukorrhiosis. 1 minus m will, of course, be shared, distributed across either stroke or healthy tissue. So I have another parameter here, beta, which is the probability of stroke if it's not a leukorrhiosis, right? It's not probability of stroke, it's if it's not leukorrhiosis. So the product of these two gives me the probability of stroke, and the product of these two, it's not leukorrhiosis and not stroke, gives me the probability of healthy tissue. Okay, this is my prior, and I have the likelihood. And so if we were done, then I would say, and now we'll use EM, and of course there are some complications. Let me tell you about how we build the optimizer and so on. Except I still need to define how we generate this MX, which is the image of probability distributions for leukorrhiosis. And specifically, we're going to do it through PCA. And so there are two parts to it in some sense when you're going to implement this, for example. One of them is when you're doing segmentation of new image. So when you're doing segmentation of new image, these purple terms, the mean and the eigenleukorrhiosis maps, are fixed, okay? They got learned before we started. And so my model is that this MX is a linear combination of the eigenvectors that I estimated before, and alpha is a Gaussian distributed according to, and of course I messed up, it's 0 here. The shape, the mean is taken by the mean. Here it's 0, and this is a diagonal matrix that tells me the variances, you know, the usual standard PCA modeling. Every entry in the diagonal matrix will correspond to the variance of the corresponding eigen. It's basically an eigenvalue in that direction. Okay, so this is what happens when I'm doing it. But behind the curtains, before you even gave me the new image, the way I estimate this mean image and the eigenvectors, we do that by taking several images, in our case it's 40, lining them up in a common coordinate frame, and then using segmentations of leukorrhiosis, tiny bit smoothed, to construct the PCA model. This is a fantastic abuse of everything you were told about PCA, because the space of images is not linear. You have no business averaging binary maps. and taking linear combinations of those maps and so on and on and on. But we just do it anyway. So there has been research in this field on doing something more appropriate, and specifically what sort of the approach that has been demonstrated by Killian Cole and Sandy Wells is to work in the space of log odds. So if you think about it, probabilities add. If you take logs of these probabilities, probabilities multiply when you want, for example, to evaluate the joint distribution of something. You take the prior and multiply it by likelihood. If you take the log of it, they add. So if you work in the space of logs of probabilities, you end up with the additive model. So at least you're not being crazy by taking linear combinations of those and constructing a PCA space. We have tried it on this problem, and it does worse. And our explanation for that is that it works better if you have one convex sort of blobby object that you're trying to model. But the log odds representation still doesn't take care of the fact that it's a shape, that if you take an average of two shapes, you are not guaranteed to get a single shape. If the shapes are close to each other and blobby, when you take average of two shapes and threshold at 0.5, you still get roughly something that is most likely is the shape. If you take a field of the speckle and you average a few of them, it just falls apart. You know, you end up with gray mush. So we've tried that, but it doesn't work. And so we just stuck with the simplest thing possible, which again is abuse of technology, but it captures something about the idea of how leukorrhiosis occurs in the images. So one thing to notice is that if you took just the mean, it would give you average frequency, either frequency or probability of having leukorrhiosis somewhere. So if I go back to my image here, right, if you went somewhere close to the ventricles, that number would be very high, and as you move away, it would decrease. But what it doesn't capture is that if this pixel is leukorrhiosis, very likely stuff here is also leukorrhiosis. This is why we need PCA. Okay? Just taking the mean will tell you how it behaves as you go away from the ventricles, but it also does it symmetrically and sort of in a correlated way front and back, and that's what the PCA captures. It's not there just because we want to use it. Okay. And then the tissue smoothness prior, again, we're abusing the Markov random field a little bit, in that we're just adding this term or multiplying in a space of probabilities to our expression. So in one particular pixel, we'll do this as a product over all pixels. We're not, right. So the product here, you need to multiply it by over all pixels. The term for one pixel is, so this is the trick that I talked about in the morning. We'll take pi, and we'll raise it to the power of, and so this should be of C, of course, to the power of that cluster of C. So let's talk through what happens here. So if my pixel is, say, leukorrhiosis, then the first element of C is 1, the second element is 0, and the third element is 0. So that selects the first element of pi, which is the prior on leukorrhiosis. You can see how if the 1 sits in the second location, it would select the second element of pi, which is exactly the prior on stroke. So it's a nice algebraic trick to then allow you to differentiate things and integrate them and pretend that this is all nice algebraic expression as opposed to case expression that is unmanageable. Okay, so this is the prior. And this term we add, which is the Markov random field term. So this y is one of the neighbors. So basically, it's a product over all neighbors, not all voxels, obviously, of C transposed AC. So this is x and this is y. This is another algebraic trick. So because this is C transposed AC at some other voxel, it basically gives you a sum of all possible products, right, of entries of Cx and Cy multiplied by A. So basically, it gives you a sum there in an exponential that has element of A, and then say this voxel is leukorrhiosis, and the voxel next to it is stroke. This voxel is white matter, and next to it is white matter, and on and on and on. And so then you can actually set A according to your preferences. So again, penalize things that are different in the neighboring voxels more than if they're the same. And so what we do here is actually we penalize neighboring stroke to leukorrhiosis much more than healthy tissue with stroke or leukorrhiosis. And those are much more than being the same value. So this A is also a parameter of the algorithm, which we don't try to estimate, we just play with it until it works. And so what we did was we played with it in 3 images and then applied it to 200 without changing the parameter. Okay, so once we have this model, we need to optimize. And so what we are doing, as I already explained, is we attempt to write an EM algorithm for this particular probability model. And the problem is twofold. One of them is the Markov random field, but there have been many, many prior papers on Markov random fields coupled with EM estimation. And effectively what you do is instead of doing closed form solution, you run mean field approximation for the Markov random field. In our case, the extra complication is that PCA space. And when we first started working on it, it was like my dream. For the first time, we would have a closed form solution to something. And it turns out we can't, because while the PCA space is linear, and we can estimate alphas, the effect of alpha, these shape parameters, let me go back and show you where alpha sits, right? It multiplies the eigenvectors. The effect of these alphas onto the image is not linear, because it gets pumped through the likelihood model. So again, we couldn't integrate over alphas, which is the proper thing to do. So instead, we resorted to point estimate, meaning that we estimate the most likely alpha. And it turns out that because PCA space is linear, it's equivalent to weighted projection. And the reason why it's not just projection, but weighted projection is because we have those eigenvalues. So you want to penalize errors in different directions in this projection differently, that's all. So what happens mechanistically, and so what this algorithm gives us is estimates of all the parameters that nobody cares about, and the posterior probability distribution in every pixel of how likely that pixel is to be leukorrhiosis, stroke, or healthy tissue, okay? So this is a standard approach to sort of optimization using EM algorithm. You pretend you want to estimate the parameters, you run the algorithm, you estimate the posterior probability distribution using these parameters, and you throw the parameters away. Because nobody kind of cares about what the distribution is of intensities given certain class. Everybody cares about what's the likelihood that it's a healthy tissue, okay? So this is exactly similar to what everybody else is doing. Mechanistically, so suppose you don't know what EM is. I'm going to tell you what the algorithm does, and you can understand it without knowing EM. So it's an iterative algorithm given the current estimate of posterior probability distribution. And by posterior probability distribution, I really mean the confidence between a number between 0 and 1 for every tissue class, and they add to 1. Okay, so given that from the previous iteration, we project onto the PCA space to estimate the shape parameters for this distribution. And we run the mean field algorithm then with these new parameters to take care of the smoothness. Now that we have all the, and so as small part of the estimation of the shape parameters, there is also the re-estimation of the intensities. So basically, you can think of this as, I have the posterior probabilities and I estimate all the parameters. And then there is another step here as part of estimation of the these two steps are part of estimation of the parameters. And then there is the next step, which is knowing the parameters, estimate the posterior probability distributions, right? And it goes back and forth between estimating the parameters and estimating the posterior probability distributions. Okay. And so let me show you results, but before that, I'll talk about registration. So as I mentioned in the morning, registration is a tough problem, and it participates in almost every segmentation algorithm without oftentimes the readers realizing it. So, and the way it participates is that in order to construct this shape model that I talked about, I actually have to line all the images up and know that I'm averaging over the corresponding pixels. When I have a new image, for me to transfer that knowledge onto the new image, I have to have it in the same coordinate frame, in the same coordinate system. So it's a tough problem. As I mentioned in the morning, we basically probably spend more time on registration than actually segmentation in this problem. Because these are clinical images, and I'll talk about it in a second. These are clinical images, almost nothing works on them out of the box. We spent months sort of doing the registration. Our original version registered these T2 images to the anatomical images. When you see images of the brain, most of the time it's T1 images that show you the anatomy much better. So registering those using some sort of rigid or defined registration, and registering T1s to the atlas that is constructed in space of T1s, and then dragging everything there and doing it there. And recently, we actually have been able to construct good T2 image. The problem with T2 is it doesn't show all of the tissues as well. There's no contrast between white and gray matter nearly as well as in T1. And so most atlases are constructed with T1 images. So we built an atlas with T1 and we registered directly to T2, sorry, from T2. And we build an atlas that way and register that way. It's a little bit better. The problem again is because there is no contrast in some parts, it actually creates challenges for segmentation. Now we're working on new ways to do registration. I should also say that we're using ANT's package from UPenn to do all of this registration. It took us a few months to actually find a good set of parameters for these clinical images, but it's a great package. Anybody who doesn't want to spend years developing their own registration algorithm, I recommend using ANTs and spending months setting the parameters. So let's see. Our data, and so let me talk about the results, and specifically, we are, as I mentioned, part of this large multi-institutional study of stroke. So right now we have about 1,000 images and sort of right now as we speak it's being grown to about 4,000 images because different sites are starting to contribute. We trained the model on 40 images that registered very well to the atlas because the worse your registration is in the training data, the looser your model is, the less helpful it is. So it's not necessarily images that have less leukorrhiosis, but it's the images that registered very well. And our test set will be 200 patients from this on which clinical experts created segmentations of leukorrhiosis by doing thresholding and manual cleanup for every one of them. And so for each patient, we have anatomical scan, axial, T2, and manual segmentations. I should say that anybody who works on brain imaging, this should send them screaming out of the room. So basically, out of the box, as I mentioned, no registration algorithm will work on images like that, right? They're so, the slices are so thick that there is absolutely no continuity from one slice to another. The structure shift like that because it's 7 millimeters difference in the sampling. So let's see, I'll show you a bunch of pictures and then a bunch of graphs that actually quantify the results. These are the example segmentations, and so I already showed this one as an example. So this is a manual segmentation that I showed you at the beginning. So an expert actually outlined them. This is our automatic segmentation. I should say that the reason why everything else looks kind of choppy is because we segment the white matter, right? So this gray kind of dull label is the healthy white matter. Okay, so what you're seeing is a very faint image, and on top of that, there's healthy white matter, and we're showing the outlines here, again, in yellow and blue, so that you can look at them and say, oh, this looks pretty good. So this is our sort of, I'm actually comfortable saying this is our typical example at this point. Now, what you can't see is the contrast here, but I want you to compare these two. Our healthy segmentation of the tissue is quite off in the area of ventricles here, right? So look at the ventricles. This segmentation should go like that. For this particular subject, it had no effect on segmentation of the leukorrhiosis because this particular subject happened to have no leukorrhiosis in these areas. If there were, it would be a problem because we would actually completely miss that part as somewhere where you should look even. Okay. So here's the quantitative evaluation. For 6 subjects in the study, our clinical colleagues keep these 6 subjects as a training set for their segmentors, the human segmentors, right? So everybody who goes through training to segment these images has to do these 6 subjects, and they do inter-expert variability analysis on these 6 subjects. And so we stuck our algorithm in it to compare to evaluate how we do relative to other manual segmentations. And so I should say that the reason why it's one-dimensional as opposed to images is because what they care about at this point is measuring volumes. So the measurements here are all in volume. So we'll segment the leukorrhiosis, but then look at the volume of leukorrhiosis as a marker of how well we're doing. And so I should say, so the gold standard is the super expert segmentor who declared themselves the gold standard, okay? So in some sense, there is very little difference between the blue circles and the blue diamond, and that all of them are just humans doing the segmentations. Okay, but the orange dots are our algorithm, and you can see that in all the cases we're within what the humans disagree on. This is but this is available only in 6 subjects. In 200 subjects, we have just 1 person segmenting it. And so we did similar comparisons. So here, there are 200 subjects. Each dot is a subject. 1 expert segmented it, and so this is this line. And our algorithm is on this line. So mostly it's decent alignment, and there are 2 subjects that are a mess, right? So either we missed the leukorrhiosis, or we said there is lots of it when there wasn't much. And we looked at them, and so let's see. This one, I'll show you, I think, in a second, is where we misclassified the stroke for leukorrhiosis, and so it's still a problem. And in this one, the registration failed. So we're working on methods to improve so you can push registration, but what we're working on is actually detecting when it is not good enough. And so it's another interesting direction of research. It's telling the humans when the algorithm failed. Okay, and so I can talk about this in the usual research talk, but I thought that for sort of summer school especially, it would be useful to show sort of the outtakes, right? It's the kind of slides that you oftentimes don't see. So this is sort of the guts of the algorithm. This is example for 2 different subjects, and I apologize for the images being so dark, but I hope you can sort of see the ventricles, yes? If you look kind of like closely, this is the ventricles. So what I'm showing you here is for 2 different subjects that are part of the algorithm, what the projections onto the PCA space look like. So just to show that it actually is doing something reasonable, right? So it's whatever subject leukorrhiosis distribution was, when you project it onto the space, it sort of puts it, so probably this subject had less leukorrhiosis than this one and puts it here. But it also illustrates problems. So you see how chopped off this is here? Like normal subjects are not chopped off like that. And the reason why it's chopped off is because the registration there put the boundary of the white matter where it's not supposed to be, right? So if it actually undersegmented the white matter, then we lost part of the leukorrhiosis. And so again, we're looking at detecting these. Okay, perfect. This actually shows up. Great, I was nervous about the slide. So here are some iterations of the algorithm. So this is the subject, and the box here is showing you the area from here. So you would expect stuff to show up here and the stuff to show up here. Okay, so this is leukorrhiosis, this is stroke. This is iteration 1, iteration 2, iteration 3, iteration 4, 5, and 6, okay? And so the colors correspond to the probability that that pixel is either leukorrhiosis or stroke. And so at the beginning, when you just use the intensity, so the initialization is just using the intensity of the images, you can see that the evidence for leukorrhiosis and the evidence for stroke is nearly identical. And that's how it should be, because effectively everything we know, the probability distributions for, the histograms of intensities look almost indistinguishable for the 2 classes. But then what happens is that this map gets projected onto the PCA space. And so the influence in this location gets reduced because there is no symmetric location. And the PCA map, if you look at it, one of the striking properties is that it's all symmetric. Again, learned from images. And so because there is no evidence here, these numbers get reduced. And when we go through several iterations, they get reduced more and more and more. And so the evidence for stroke starts, so this is just the intensity. But once you get to the projection, the sum of this and this stays roughly constant, except for, and therefore, as the evidence for this island in leukorrhiosis decreases, the evidence for stroke grows. Because stroke wants to take up those voxels, because they are from that intensity distribution, so they don't look at all healthy, and leukorrhiosis doesn't want to take them in, okay? And so this is really what's happening in the iterations of the algorithm in a single case. Okay, and so here's where it didn't work. And again, this example this registration, I apologize, it's very clear on the slide, but somehow doesn't show up here. The ventricles go like this, and so this is the case where I showed you that we got lucky in some sense, in that the segmentation was correct, but we use it as a failure case exactly because we think that if this particular patient had leukorrhiosis along the boundary of the ventricle where we failed, we would have failed in segmentation. So thinking about how to change this algorithm so that it can pay attention to the boundaries in the real case as opposed to the atlas would be great. And we also fail when there is dramatic amount of leukorrhiosis. And so we realize that actually that happens because our training set doesn't have any examples of dramatic spread of leukorrhiosis. So we're hoping that we can fix this by adding more good examples. The problem is that these cases tend to misregister as well. Again, look at how sort of the ventricles are just a little bit too big for my taste. So the problem is that cases with lots of pathology register poorly. So it's tough to include them in a training space. If you don't include them in the training set and train your model on them, then your model doesn't want to see anything like this in the images and guides you away from that. And so here, instead of allowing us to call everything leukorrhiosis, it declared a bunch of stuff stroke and just kind of threw its hands up. So again, I think it's important to work on the algorithms to improve stuff, to improve the accuracy, but it's also very important to understand and identify where they fail. Okay, and so here's a little preview of what we're doing with it for population analysis. This is very simple, has no genetic data. This is just with age. So if you plot the volume of leukorrhiosis as a function of age, and I should say, especially if Guido is in the room, this is not longitudinal. We only measured every patient once, right, when they had the stroke. So it's a snapshot of every patient. It's not tracking patients over time. Okay, so every point corresponds to a patient. And when you look at it without even all of these plots, it's striking how there is just a thick line that is almost horizontal in terms of the volume of leukorrhiosis, and that there is stuff that starts growing. So we ran the clustering on these, so the typical clustering, like if you think about clustering in general, it clusters the values. What we cluster is the slope. Right, so we assume that there is a linear growth in leukorrhiosis volume, and we look for two clusters with two different slopes. It's exactly the same as regular EM clustering or k-means clustering, whatever you prefer to use, but it clusters on the slope rather than on the value itself. And so these two lines are the result of that. It's basically linear regression, but in two compartments separately. And then these, don't try to read them, I'll show them to you on a different slide. But effectively, our goal is to create a representative patient at that stage in that cluster. And so here they are. The way we do this is through an algorithm called shape regression. It's probably about 10 years old at this point. And the idea is that you take patients, so for example, you want to represent typical patient, typical subject at this age. You take all the images around, you register them together, and then you take a linear combination that weighs images based on how close they are to based on the age, right? Like how close their age is to the images. And so in the first one, there is hardly any accumulation of leukorrhiosis. In the second one, leukorrhiosis grows substantially, which is not surprising having seen the first plot, right? So now we can start doing interesting things, and we're about to do them as look at clinical information in the second cluster and see what's different in that second cluster from the first cluster to understand why is it that some people accumulated and some people at 70 have as much leukorrhiosis as some people at 20. Okay, so before I conclude, I want to thank my co-authors on this work, Adrian Dalka and Ramesh Sridharan. As I said, we have a very good collaboration with Mass General Hospital on this. Adrian will be presenting this talk at Mackay this year. Well, not this talk, this work. He'll do a much better job at it too. Okay, and we're supported by 2 large grants that are aiming to develop biomedical image analysis projects. So to conclude, what I showed you today is an approach to segmenting pathology, which is always difficult because it's hard to capture variability in pathology. And we did this by looking at the images and understanding what properties of the pathology actually repeat across subjects. And specifically, we capture it with the PCA model of spatial variability of leukorrhiosis. And that allows us to distinguish between leukorrhiosis and chronic stroke that are virtually identical intensity-wise in the images. And sort of, I'm very happy about this because it's sort of very particular application domain with very particular pathology, but we could use very general algorithms and get quite decent results. Interestingly enough, the algorithm itself is of interest to a broad set of clinical scientists who are studying different diseases. Because it turns out that this leukorrhiosis plays into not just stroke, but multiple sclerosis, normal aging, and many other diseases. So we're now actually in conversation with a couple of groups that want to study, that are studying it using manual segmentations and are kind of thinking about how to scale it to thousands of subjects and want to use something like this. And finally, in the future, current and future, we're working on improving the registration. The next big leap we're going to make when I'm back is we're actually going to apply all of this to about 7 different sites that have been collecting subjects as well. And we find out how our beautiful model breaks when you start applying it across sites. And we'll have amazing insight on how to fix it. And then the next talk, of course, we'll talk about how that was the most obvious thing. This is in reference to how Ramin said how these technical talks go. It's always a set of iterations. And finally, the final goal is to do this joint analysis of imaging and genetic information. And this is what we're starting to work on right now. It's quite an exciting area because we're hoping that that will combine medical imaging with fundamental research into the causes of the disease and genetics. Thank you.